Yeah, I guess people will trickle in as we move along here. So here we go. Any thoughts on the midterm? Yay, nay? Is it fair? It's good. It was all right. Yeah, a lot of stuff from the homework, right? So good stuff to see. All right, so what's the plan today? I thought I was going to get through 5 sections. I got through 3.5. So we'll see how long this takes, but hopefully I can get through more with a smaller class. So let's go through bases first, and we're just going to talk about bases real briefly. So what we really care about today with bases is let's just talk about the standard basis of a vector space, right? So a standard basis of a vector space V is a basis that seems the most obvious. Like, there's really no better way to put it. It's just, all right, here's a vector space. What is obviously like a basis that we have to define for this vector space? So, I mean, if we go through examples, you can see this clearly. So Rn, right? The standard basis for Rn is going to be, well, 1, 0, 0, 0, 0, 1, 0, 0, and then all the way down to 0, 0, 0, 1, right? So pretty obvious that, that's what we're going to choose a basis for Rn. What else? Polynomials P and R, all right? That's another basis. Another vector space that has a really clearly defined standard basis, and 1, x, x squared, etc., all the way up to xn, right, is pretty clearly going to be a basis for P and R, all right, the polynomials. What else? M and R, square matrices, all right, also have a well-defined standard basis. You can think of this as like 1, 0, right, 0, and then 0 everywhere else, and then 0, 1, 0, 0 everywhere else, and then all the way down to 0, 0, 0, and then 1 in the bottom left corner, bottom right corner. Okay, so these are going to be your standard bases for some vector spaces, and again, they're standard bases because they're like pretty obvious. Okay, so given the standard basis, another definition that we need to define is going to be dimension. Okay, and what is dimension? Dimension is the number of vectors in any basis of a vector space V. And then this is the dimension of V. Right? So for any vector space, we're going to have a basis, and there can be multiple bases for a vector space. All right? And so we'll get down to the idea that a vector space has multiple bases in a bit. But the one thing that's going to stay consistent across every basis is that they're all going to have the same number of elements in those bases. All right? And so then the dimension of that vector space is going to be V. And so, for example, then, what are the dimensions of, let's say, Rn? Yeah. N, right? Because there's going to be n of these vectors in there. All right. What about P and R? N plus 1. Okay. So big deal is this constant term here. A lot of people forget it. The dimension is n plus 1. And then what about the dimension of square matrices? Yeah. N squared, exactly. So remember, it's an n by n matrix, so you have n squared entries, and then you put a 1 in every single entry. So those are going to be your standard bases, and then your standard dimensions as well for those vector spaces. Okay? All right. Lastly, let's talk about a theorem that's going to be really useful I guess it would have been better to talk about this last week, but we'll talk about it now since you can also hand in your recitation homework on Friday. If a dimension of a vector space V is n, and you're given n linearly independent vectors inside V, then first of all, they span V. And then, okay, so what do you have? Well, you have n linearly independent vectors that span V, which means that they form a basis. All right, so a lot of times if you already know the dimension of the vector space that you're in, all you have to do is show linear independence for the number of vectors you're given, right? So if I give you 4 vectors in a 4-dimensional space, all you have to do is show that those 4 vectors are linearly independent, and then they automatically span by this theorem, and then they form a vector space. They form a basis. All right, it can go the other way as well. So if you have like n vectors in an n-dimensional space, and you know that the n vectors span, then you know that they're automatically linearly independent as well. Okay, so you can start from either hypothesis. You can start from one, or you can start from the hypothesis. But once you show that the other is true, they automatically form a basis. Okay, so this cuts down the work you need to do by a little bit, because if you show linear independence for these guys, you don't have to show span. Any questions about this theorem? And that's pretty much all about bases I'm going to talk about for this recitation. All right. So from here on out, this is pretty forward-looking now in terms of what we're going to cover. So a lot of the stuff you haven't even covered yet, you'll probably cover tomorrow in class. So let's just start here then. Coordinates and change of basis is section 4.7. All right, and the idea is the following. So in recitation, or in lecture yesterday, you started looking at coordinates, and so we'll do the same thing here. And by looking at coordinates, then we can motivate change of bases. So let's say I have these 2 axes, right? And let's say that, so we're in R2, right? We're in 2-dimensional space, and we'll define a basis on the 2-dimensional space, and we'll let that be 1, 0, 0, 1. Okay? And so E is going to be the name of that basis, and that's usually what we name standard bases. All right, so this is the standard basis for R2. Okay, and we can pretty clearly see that these axes represent the standard basis 1, 0, 0, 1. Okay, so now let's take a vector 3, 2. Right? So that's 1 and that's 1. All right, so why do we even call this vector 3, 2? Well, the idea is the following. This point, right, can be represented as 3 times 1, 0 plus 2 times 0, 1, right? Pretty obvious. And therefore, we give the vector, or this point, or this vector, a coordinate, and we say it's 3, 2, right, with respect to some basis E, right, or respect to our standard basis E. Okay. But now, what if we're interested in some other basis for R2, right? Because right now I just gave you the standard basis, but we can be funky and we can change things up. So let's say now we take this new basis. All right, looks like this in the purple. Okay. So we'll define this basis to be B, and the vectors that describe this basis are going to be 1, 2, and negative 1, 2. Okay, but now the question is the following. How do we describe then this point here? What are the coordinates of this point with respect to my new bases? Right? And because we're in R2, we can actually just eyeball this. So can anyone like see what we should get? Yeah. So we should get 2, -1. Okay? And the idea is, all right, so here's 1, 2. Here's the second one, and then we come back down, right? One of them. Okay, and so, right, so this can be written as 2 times 1, 2, plus a -1 times -1, 2, right? And so now we say that this point has the coordinates 2, -1 in basis B. Okay, so just by defining our bases differently, we can express the same point as different coordinates. Right? And so that's the idea. Any questions about this? Okay, so this is all good because we can eyeball. We can just eyeball the solution. But what if we can't eyeball the solution, right? What if we're only given like some basis elements, and then we want to actually find that point with respect to some different coordinate? So that's what we're going to talk about now. No rule lines. All right. So how can we find coordinate vectors in a basis C given the coordinate vector in another basis B? So for example, if I told you that this point was 3, 2 with respect to the standard basis, how can you tell me that this point is going to be 2, -1 with respect to my basis B? All right? And this is where we bring in change of basis. So here's what the problem statement of these problems usually look like. Example. Let E be some basis, 1, 0, 0, 1, all right, the standard basis, and B be 1, 2, -1, 2 bases for R2. Okay. Let V sub E equal 3, 2. All right. So this means the coordinate with respect to basis E. All right, with respect to basis E, find VB. All right, so now we want to find the coordinates with respect to basis B. So literally, all we're doing is up here, what we did in this drawing up here, but now we're going to do it formally through matrix algebra. So how do we do this? Okay, that's how we do it. VB is equal to a change of basis matrix from E to B times VE. Right, so you take your original coordinate, there's some change of basis matrix that multiplies that coordinate, and then that gets you over to your new coordinate system. Okay? So this is the change of basis matrix from E to B. Right? So you start at E and the arrow points you, says you're going to B. All right? The book notation writes it like this, which absolutely makes no sense because how do you know where you're going? All right? And so I think McGrath does P from E to B, rather than the book notation, but just keep in mind that that's what the book notation is. I'll alternate between the two a lot just so that you can, when you see this, you'll think this. Okay. So how do you find P from E to B? Right. Well, what really happens is the following. You solve a system of equations that, so here are your B basis, and then there's some matrix that you multiply to get over to the E basis. Okay? And this matrix that's multiplied is the change of basis matrix. Right? And Professor McGrath might introduce this in a different way tomorrow. He might introduce it in like a linear combination type of way. But just know that this is essentially what's going on. So to find this matrix, what we can do is we can actually just put together an augmented matrix where we put our basis B on the left and we put our basis E on the right. Okay? And that's why this notation is so good, is because it literally tells you what goes on the right and what goes on the left. Okay? Now what do we do? Well, the goal is to reduce the left-hand side down to the identity matrix, and the right-hand side will give you the change of basis matrix. Okay? So in this case, right, we'll reduce 1, negative 1, 0, 4, 1, 0, negative 2, 1, 1, negative 1, 0, 1, 1, 0, negative 1 half, 1 fourth, and then 1, 0, 0, 1, 1 half, 1 fourth, negative 1 half, 1 fourth. Okay, so we get the identity matrix, and then here is P EB that we wanted. Okay, but notice what we kind of did here. We kind of just took the inverse of a matrix. This is actually just a coincidence, all right? And so it's because we started from the standard basis and we went to some other basis. So if you ever start from the standard basis and you change to another basis, it's just going to be taking an inverse, all right? So starting from a standard, and going to basis B is just taking an inverse. Okay, so again, this is completely coincidental. It just happens to work out this way because if you just look at our setup, right, this is the identity matrix on the right-hand side, so we're just finding inverses. But in general, that's not going to happen. Okay, so we found our change of basis matrix. What do we want to do now? Well, remember this formula right here, right? Our entire goal was to express this vector in terms of the coordinates in basis B. So let's do that. So now VB is equal to PB, right? P from E to B times the coordinate vector of E. All right, we have our change of basis matrix that we found from above. All right, and now VE was 3, 2. Right, VE was 3, 2. That's given to us. All right, and this is equal to VB. So now we just need a matrix multiply this out, get our answer. What do we get? 3 halves plus 1 half. That's 2. Negative 3 halves plus 1 half. That's negative 1. All right? Yeah.
Why is it better to do this way instead of just like finding a linear combination of like the first vector
This algorithm with the augmented matrix, I think it's a little better for larger systems. And also, you'll see an example coming up right here. Sometimes you need to do special things with your linear combinations that might not be immediately clear if you're just taking combinations. All right? So, right, we get 2, -1, which is exactly what we thought we should get, because if we look at our eyeballing, right, that's what we got. We got 2, -1. And here's the mechanism that shows you the correct way to actually do it, rather than just, hey, look, we can see it. All right? Any questions? Okay, so a few notes before we jump to another example. All right. 1, if the basis is unstated, assume standard basis. So, for example, I wrote VE, right? But almost no one ever writes VE because they'll just tell you it's V. All right? So if this vector right here was just like V equals instead of VE equals, just assume that that was given to you in the standard basis. Okay? And this actually happens on the homework. So number 6 on the homework. You're given a bunch of just like regular like vectors, and McGrath asks you to like express it as a coordinate in some other basis, but he never gives you like the original basis, so you just assume the standard. Okay. Number 2, order of basis elements matters. Okay. As you can tell from this row reduction up here, right? If I switched 1, 0 and 0, 1, right? I'm not going to get the same change of basis matrix. Okay. So it really matters where you put your, like, the order of the bases you put in the matrix. Don't randomly switch orders of bases. You're going to get the wrong answer. So keep that in mind. Number 3, all right, if you find this guy, right, if you find the change of basis from B to C, well, you can find the other guy by just taking an inverse. All right, so if you know C to B and you want to find B to C, just take the inverse of C to B. All right, so that's a nice property of the change of basis matrices. And number 4, change of basis happens in the same vector space. Within the same vector space. All right, what does that mean? Well, does the dimension of a vector space ever change? No, right? Because the definition of dimension is, right, the number of elements within any basis that it give you. So the number of basis elements will always be the same, right? So if I give you some basis B, it's going to have the same number of elements as in basis C. All right? What does that mean? That means P is always a square matrix. Always. It's always going to be a square matrix. Okay? P is always going to be a square matrix. If you end up with a non-square matrix, you're doing something wrong. Because what we'll learn a little later on is that non-square matrices are actually maps from one vector space to another vector space, right? But if you want to stay inside the same matrix, you want a square matrix so that the map is within the same dimension. So what does this mean? This means if you have too many rows, get rid of some of them. And we'll see an example right here about how to do that. Okay. Example, spring 2016 final. Fun fact, I took this final. So, I'm pretty sure I got this problem wrong too, and now I'm teaching it. So you're given bases for 2 by 2 matrices where A21 is equal to 2 times A12. So you have some matrix, right? A, B, and then so this has to be like 2B, and that's C. So that's what the general element looks like. Here, here's a basis. So here's basis B, which is equal to 1, 0, 0, 0, 0, 0, 0, 1, 0, 1, 2, 0. Okay, and then basis C is 1, 1, 2, 1, 1, 0, 0, 1, 0, 1, 2, 3. All right, part A of the problem says prove that C is a basis for the subspace. But we're going to skip. We're just going to skip this part. All right, so this is some subspace of M2R. And then part A says show that C is a basis, so you just have to run through linear independence and span, right? Why can't we use the theorem for part A? Right, remember that one theorem? It was like if you know the dimension and you know that they're linearly independent, then they automatically span. Why do we have to show independence and span like explicitly? Well, the question is, how do you know that that subspace is dimension 3? Right? Because it's like A21 is equal to A12. You can give some argument why it's dimension 3, but in general, like just because we give you 3 elements in C, it doesn't mean that that's like enough, right? It could have been in like a 4-dimensional space. Yeah.
Oh wait, are we given that B is a basis of this space?
I don't remember how the problem was exactly worded. Yeah, if they said B were a basis, then yeah, you can just say it's dimension 3. Yeah. So give some argument why it's dimension 3 and then show linear independence, right? That's all you need to do. Or you can show it linear independence and span. Okay, not going to do A. Let's talk about B. All right, find a change of basis matrix. PBC, all right? And this is how the problem was actually given. So when you see PBC, you really want to think that guy with the arrow. Okay, so now we run into the classic case of I have matrices that I need to put into other matrices, right? So remember, when you have matrix and you want to put them in as a column vector, you got to unravel the matrices, right? So in this case, let's write B as the following: 1, 0, 0, 0, 0, 0, 0, 1, 0, 1, 2, 0. Okay, so right, 1 goes here, 0 goes here, 0 goes here, last 0 goes down there. That's how we're unraveling these. All right, and now C is going to be 1, 1, 2, 1, 1, 0, 0, 1, 0, 1, 2, 3. Okay. Let's create my augmented matrix. Right? What goes on the left? C, right? Again, this notation, really helpful. C. So 1, 1, 2, 1, 1, 0, 0, 1, 0, 1, 2, 3. And what goes on the right? B. Right? So 1, 0, 0, 0, 0, 0, 0, 1, 0, 1, 2, 0. Okay, what did I say about the change of basis matrix, like, before we started this example?
Square.
Yeah, it needs to be square, right? So, are we going to get a square matrix if we reduce this? No, right? So what did I say about what happens if you don't think you're going to get a square matrix? Yeah, some row needs to get deleted. All right. So if you look at our matrix, or look at our augmented matrix, and this is why you want to kind of do this instead of the linear combination type stuff, because it's not as immediately clear that you need to like get rid of something. Okay, so what should we get rid of? Second or third row. Why?
Because it's multiples of each other.
Exactly. Second and third rows are multiples of each other, right? So for sake of things, let's just get rid of row 2. Okay, and then we're going to note that, right, because remember, row 3, sorry, we're going to get rid of row 3. And remember, row 3 corresponds to the third entry in our matrix, right? And so we just make a note to ourselves that the third entry of our matrix is always 2 times the second entry, right? Because the third row is just 2 times the second row. Equals 2 times second entry. Okay. So now, a little more manageable. 1, 1, 0, 1, 0, 1, 1, 1, 3, 1, 0, 0, 0, 0, 1, 0, 1, 0. All right, now we have the square matrix. We just reduce down to the identity on the left and the change of basis on the right. So I'm not going to do the work, but there's the identity. And then you get 1/3, negative 1/3, 1, 2/3, 1/3, negative 1, negative 1/3, 1/3, 0. Okay, so identity in P, B, C. Any questions? All right, so part C asks you to write this matrix, 0, 2, 4, 0, in terms of basis C. Okay, so since this is part C of a question, we should probably use part B. So we know what P from B to C is. All right, so now we essentially want to find some coordinate vector in terms of basis C, and that's going to be equal to the change of basis vector times the coordinate vector in basis B, right? Okay, the problem is, what the heck is this? So step 1, find 0, 2, 4, 0 in terms of B. Okay, so we need to find that matrix in terms of basis B. How do we do this? Well, okay, we look at our basis B, right? And our matrix is 0, 2, 4, 0. What's a linear combination of the B bases elements that can get me that?
0, 0, 2.
Yeah, 0, 0, 2, right? So essentially, right, 0, 2, 4, 0 is equal to 0 times 1, 0, 0, 0 plus 0 times 0, 0, 0, 1 plus 2 times 0, 1, 2, 0. Okay, and so just like we did before with in R2, right, we just take these coefficients and now we throw them into a vector. All right, so VB is 0, 0, 2. Any questions? Okay. And then now, right, step 2, okay, now, right, VC is equal to PCB VB, so that's equal to 1/3, negative 1/3, 1, 2/3, 1/3, negative 1, negative 1/3, 1/3, 0. Okay, Just making sure I have the right change of basis matrix because I have a negative sign on one of them. I don't on the other one. Okay, just copying error. Okay, so that's that. And then, right, what is VB? VB was 0, 0, 2 that we found above. And so if we multiply this out, VC is 2, negative 2, 0. Okay, and so what does this mean, right? Well, it means that 0, 2, 4, 0 is equal to 2 times the first basis element, which was 1, 1, 2, 1, right, of C, minus 2 times the second element, which is 1, 0, 0, 1, and then plus 0 times this last element, 1, 1, 2, 3. Okay? And so, given all this, we know that the basis elements, well, there's your linear combination of VC in terms of, or there's a linear combination of 0, 2, 4, 0 in terms of the basis elements of C. And again, order matters because if you like switch these guys, then this vector would be like 2, 0, negative 2, right? So the order of your bases like does matter. Okay, any questions about change of basis? So on your homework, there's like some very specific change of basis types of problems with regard to the, what was it? The partial fraction stuff. So make sure you're paying attention in class when McGrath is talking about partial fractions and how to like set up bases for those. Okay, 4.8 is going to be row space and column space. All right, start this off with some definitions. Definition of row space is going to be the following: the span of all the rows of a matrix A. All right, and column space is exactly what you think it is. It's the span of all the columns of a matrix A. Okay, for row space, we usually denote this like RA or row space A, and then column space CA or call space A. Okay. So let's go to this drawing again, right, of AX equals B. Okay. So remember, A is m by n, x is n by 1, B is m by 1. Okay. If I take a row, what's the dimension of the row of that matrix? N, right? It's a 1 by n vector. All right. And what about the column? Yeah, it's an m by 1 vector. Okay. What does this mean? This means that row space is a subspace of R n. Call space is a subspace of Rm. Okay? All right, let's try to find row space and call space. Should be really fast. Okay, so let's take some matrix. 1, 1, negative 3, 2, 3, 4, negative 11, 7. All right, first step is just to reduce it until you see where the pivots are. So in this case, 1, 1, negative 3, 2, 0, 1, negative 2, 1. So you actually want this to be in row echelon form. Okay? How do you find the row space? Well, you take all the non-zero rows in row echelon form. So I have my rows. So row space of A is equal to the span of, well, this guy and this guy. So 1, 1, negative 3, 2, and 0, 1, negative 2, 1. Okay, so that's how you find row space, and here's how you find column space. Column space is the following. You use the pivots as indices for the columns in the original matrix. All right, so for example, right, I have pivot, pivot, free, free. Right? And so I go back to my original matrix, pivot, pivot, free, free, and just take the two pivot columns. So my column space is going to be the span of the two original columns with the pivots. All right, so the span is going to be 1, 3, 1, 4. Any questions? Yeah.
Why do we need to be in reduced echelon form for row space?
For row space, technically you can just take the original columns as well, original rows as well. But I actually wouldn't worry too much about row space because this is the last we're going to talk about row space. It absolutely doesn't matter. Okay. Any other questions? All right. Let's see. What is the rank of this matrix? 2? All right. What's the dimension of the row space? 2. What's the dimension of the column space? 2. Right? They're all equal to each other. All right. And that's always going to be the case. So that's an important thing to note, is that the dimension or the rank of A is equal to the dimension of the row space, which is equal to the dimension of the column space. All right? Always going to be the case. Okay, so now we only care about call space A. All right, row space is just there. Like, sure, it's cool, but we don't really care about it. So why do we only care about column space? Let's look at the following, right? So the columns are m by 1 vectors, right? As we drew up here, the columns are all m by 1. What else is m by 1 in that equation? B. Okay, so now if we do another sketch, right? Here's A, here's X, and here's B, right? Notice, all right, if I just care about the columns of A, V1, V2, V3, Vn, right? Assuming A is n by n, so there's going to be n columns, all right? X is n by 1, so we have x1, x2, all the way down to xn. All right, and then B is just whatever it's B. Okay, what does the left-hand side multiply out to be? Well, x1 v1 plus x2 v2 plus xn vn. Okay? And the right-hand side is b. What is the left-hand side? What is that? Linear combination of the columns, right? In particular, do we know what x1 through xn are? No, right? We're solving for them. So it's literally all linear combinations of the columns. Okay, what is that? It's column space, right? Because it's literally everything that the columns can hit, right? So it's the span of all of the columns, which is really just the call space of A, right, or CA. So what does this mean? This means, okay, then what is B? Well, we're really seeing if B lies in the column space of A or not, right? We really care if B is a linear combination of the columns. So what if B does not lie in the call space? Is there a solution to that system? Right? If B is not in the column space, there's no solution. There's no linear combination that can hit B. All right? So this is why we care about the column space so much, is because if B is inside the column space of A, then AX equals B is consistent. All right? And if B is not inside call space A, then AX equals B is inconsistent, so there's no solution. Any questions? So that's essentially why we care about the column space, is because the column space tells us about the consistency of our systems of equations. All right? Whereas the row space doesn't tell us anything. All right. Last section, 4.9, Rank-Nullity theorem. Okay. Really just states the following. The dimension of the column space plus the dimension of the kernel is equal to the number of columns. All right? But what is the dimension of column space? It's the rank. And this, the dimension of the kernel, we call the nullity. And that's equal to n, right? If A is m by n. Okay, so definition, nullity is the dimension of the kernel of A. Right? And if we remember what the kernel was, right? A, X, B, M, N, N1, M1, right? The kernel of A is the set of all x's, right? But x is n by 1, so it's an Rn such that AX is equal to 0. Right? So that's the kernel of a matrix. What is the kernel a subspace of? An idea? Anyone? It's R something. Question is it Rn or Rm? It's Rn, right? The set notation kind of gives it away, right? Also, x, right? Your kernel are your x vectors that make AX equals 0, right? So this is a subspace of Rn. So this is why we don't really care about row space, because the subspace of Rn that we actually care about is the kernel. All right? So call space, remember, was a subspace of Rm, And now kernel is the subspace of Rn that we care about. Oops. All right. So, I mean, that's it. 950. So really quick example. This one shouldn't take, this should take like a minute. So let's say you have this matrix, 1, -1, 4, 3, 2, -2, 8, 1. Okay? And you just want to prove the rank-nullity theorem. That's it. We just want to show that it works. Okay? Reduce it. 1, -1, 4, 3, 0, 0, 0, -5. Pivot, free, free, pivot. Right? What's our call space? Our call space is going to be the 2 pivot columns. So it's going to be the span of 1, 2, and 5, and 3, 1. Sorry, this is a 3. It looks like a 5. Okay? And so the dimension of column space is equal to 2. And what's our kernel? Well, now the kernel, you just have to solve for the null space of this matrix, right? Which is, you should know how to solve for the null space of this matrix. If you don't, again, row 2 tells us that -5 x4 is equal to 0. So x4 is equal to 0. Row 1 tells us that x1 minus x2 minus plus 4x3 is equal to 0. Or plus 3x4 is equal to 0, but that's 0. Right? x4 is 0. So now, this is x1 is equal to x2 minus 4x3. So if we let x2 equal s and x3 equal t as our free variables, right, we get that the kernel, then we get x is equal to, or the kernel is, is equal to, so x4 is 0, x3 is t, x2 is s, and x1 is x2 minus, so s minus 4t. All right, which is the span, so the kernel then is the span of, essentially just factor out the coefficients. So this is 1, 1, 0, 0, and then you get -4, 0, 1, 0 for the t's, right? So this is like the s guys, and this is the t guys. All right, and so this dimension is also 2. And then from up here, the dimension of the column space is 2, the dimension of the kernel is 2. You add them up, that's 4. That's the number of columns in the matrix. All right. That should get you pretty far in the homework. There's like one problem that I didn't cover. So I think that problem, I guess, just come to office hours if you need help. It's like a linear transformation problem. There are donuts here. Please take one if you haven't already. Hand in homework if you have it. Otherwise, you can hand it in on Friday. I think I sent an email about that. And then here are the recitation homeworks for this week.
Basically, I've done 1 and 5, and I'm halfway through 2, 4.
Did everyone get one?
So, figuring that is
Yeah, no problem. Oh yeah, take a donut, please.
Oh, it's when it's then there.
Thank you.